Thus far, we've talked about the why we even built this in the first place. We talked about the what, in particular, data programming and the AI compiler. Now let's dive into the how. And in this video, we're going to talk about the quality assurance module. Sound good? Let's get started. And for that, I'm actually going to go on our website, Super.AI.com, and I'd invite you to do the same. There's a lot of information in there, not only on the homepage, but in the documentation. So there's 138 ways in which we assess quality, but I'm just going to go over a few of them now to give you the idea. And if you're interested, we can talk about all of them. So there's 4 aspects which we analyze quality. We look at the quality of our labelers, which we talked about in the previous video in the AI compiler. We look at the quality of the task, and typically these are very simple tasks broken down with data programming. We look at the quality of the instructions, and finally the quality of the data. So let's go through a few to give you an idea. So it's really important to know that the labelers you're using are high quality, and at the very least what their quality is, so you can feed that information into the router. And so what we do is, one of the first things we do is what we call a qualification. So before a labeler can even start on any project, they need to pass a qualification. And this qualification is generated automatically. And there's 3 levels of this qualification. The first level is what we call the skill tree. And so these are what we consider basic skills. So if they're going to handle English tasks, they need to understand English, or if they're going to handle French tasks or Chinese tasks, well, we need to know that they understand this language. If they're going to do image annotations, well, we just need to know if they can use their computer effectively to draw bounding boxes or polygons, and we just want to know basically if they'll follow instructions. And so this is the first level of qualification, is skill tree. The second level of qualification is what we call the template qualification. So when you first generate a data program, we call it a template because it doesn't yet have all the specifications of your particular instance. So it doesn't have your particular instructions, it doesn't have your particular ground truth data, etc., etc. And so what we do first is we have example data that is tied to a particular template, and they must pass this first before they work on your. And so this is used before you upload any data or any ground truth data. We require that any labeler, whether it's human, machine, software, before they work on your task, they have to pass a minimum bar on the template qualifier. Finally, we have instance qualification. And so once you have created a data program instance with all your instructions, ground truth data, etc., then the person must pass as well instance qualification. So they maybe have really good skills, they can speak English really well, they may pass the template qualification, which means they're really good on this particular task on example data, but it still may not mean that they're good on your specific data. And so this last piece is really important. So that's qualification in a nutshell. We also have something which we call dynamic ground truth. And so you can imagine, let me use an analogy to how do you become a lawyer? Well, you need to pass the bar exam. So, okay, now you passed that was qualification. Does that mean you're still a good lawyer? Maybe you started slacking off and you're no longer a good lawyer anymore. Well, what dynamic ground truth does is we audit the labelers at a interval defined by our partially observed Markov decision process, which I talked about in the AI compiler video. And what it does is it sends labelers tasks which we already know the answer to. And then it checks their prediction based on the actual ground truth. And if they get it correct, then that updates their distribution of quality. If they get it incorrect, it again updates the distribution of quality, but they lose trust. So if you get it right, this updates the trust score, and this is a simplified metric of the distribution related to its mean and median, and that's not important. We can go into that later. Okay, so we do this for all the different types of labelers, and what happens is this updates their database, and it makes sure that they're continuing to be high quality. Next, we do something we call the consistency score. So this is especially relevant for humans. It's less relevant for machines, but not always the case. So sometimes humans can get fatigued. They can go into this unconscious mode where they just start clicking, or they're tired and not paying attention. And so what we do to combat that case is we'll send them a task, and then at some moment later, we'll send them the same task, but it's not exactly the same. We permute the task, either the answers, the inputs, or outputs, and then we just see if they're consistent. And if they're not, then again, we update, we decrease the trust score, and in general, we update the quality distribution. There's one thing I missed here, which I want to just go back and address in the ground truth in general is, so there's cases which you can, let's just say if the output of the task is a category, you can automatically see if they're correct by just comparing their categorical choice to the ground truth. And so that's easy, you can do that automatically. But then there's cases where the task is subjective. We try to make all tasks non-subjective, but sometimes there's a subjective task. And so since it's subjective, it needs to be graded by someone that you trust, typically a human. And so if that question popped in your head, I wanted to address that. And so the interesting thing is that for tasks like qualification and ground truth, we call these supervised because you need the ground truth. But the consistency score is unsupervised. We can use this with any data. And so this makes it very scalable and powerful. Okay, so those were measuring quality, but how do you actually increase the quality? Well, everyone, if it's human or machine, they're paid based on their performance. So it's really a meritocracy. And especially for humans, this has a huge impact on their performance. And so I don't think this is surprising. I need to go into too much detail about that, but I just wanted to mention that. And then another thing we use is a generative model. So what the generative model does is, after you've been measuring consistency scores and qualification and ground truth, you can actually learn what attributes an ideal labeler looks like and remove the labelers who don't meet these variables that are highly correlated to really good labelers. And so you want to be a little bit careful with this because this isn't perfect, but it actually adds a fair amount of signal and increases the quality quite a bit. Okay, so there's a lot more to this, but I just wanted to give you a few examples of how we assess labeler quality. Now let's move on to how we assess task quality. So the first one, and it's a classic one, is you route to multiple labelers and take the consensus. And if you remember back to the AI compiler video, this is what the combiner system does. And again, it uses a generative model. In most cases, in simpler cases, you can use kind of simpler consensus methods. And so in order to increase quality, you want to not only measure the quality of each labeler, and how many labelers there are, but you also want to measure the correlation between the labelers. Because as you know, if you have, let's just say all your labelers, even if they're really high quality, they always answer the same thing. Well, combining them isn't going to give you any benefit, right? You want them to be as orthogonal and uncorrelated as possible. And so that's what this combiner and consensus system does, is it chooses labelers who are uncorrelated, or you can say statistically independent, and decides how many, well, the router decides how many to route to, and then you route it to them, and the combiner decides how to combine it, and then you get a distribution and a summary statistic, which we typically use the entropy. And so this consensus is not only a way to measure the quality by measuring the distribution or the summary statistic entropy, so you can measure how high quality or low quality your task is, but you can also increase the quality by adding more uncorrelated labelers. Okay, we related to consensus, we have the incremental relabeling system, which when you specify what quality you want, and we talked about in the previous video of the AI compiler, that not all data is the same. So maybe one data point is very easy, and so you just need, it can be handled by an AI or a software function. But maybe there's another data point that's difficult. And so, like I mentioned earlier, we treat all data points differently. And so what we do is we start and we route to labelers we think is best, and typically it's a single labeler. And then using the methods we talked about previously, we can assess the quality, and if it's not high quality enough, we will add more labelers, and they want to be uncorrelated. And so a really difficult data point maybe could have 10 or 11 labelers, and a simple data point can have a single labeler. And so that's the idea behind the incremental relabeling system. Next, we have the anomaly detection system. And so what happens is over particular tasks, and if you condition on different types of data complexity, then you can, again, form a distribution of the quality, cost, and speed, but also the actions. And so, for example, if you see someone take a really, really long time on a particular task, or really, really short, then that triggers the anomaly detector, and then that goes into a subsequent review process. And so typically when you see anomalies, that's a good indication that that task was not high quality. And then it goes into a further review process, which we'll talk about now. So we have a group of experts, and these are in the highest hierarchy of the Super.AI labelers. It goes through a pipeline, and not only for the dynamic ground truth that needs subjective assessment, we talked about that before, but just for tasks in general and in random, and again, this is determined by the POM-DP, we have a group of expert reviewers who are constantly reviewing data. And by the way, these expert reviewers can be people in your organization. You can invite someone from your organization to be that reviewer, and that works seamlessly in the system. And if you've seen the demo, we've shown you how to do that. If not, I'd encourage you to watch the demo video. The last one I'd like to cover is what we call the likelihood classifier. And so just like the anomaly detector over time understands how long a particular task takes, conditioned on the data, the likelihood classifier does something very similar. So given, again, condition on the data points, the likelihood classifier learns a distribution of what you'd expect the answer to, what you'd expect the output to be within. And so let's say we're drawing bounding boxes on an image, let's say dogs, and we have a really, really big bounding box or a really, really small bounding box. That will trigger the likelihood classifier to throw a flag, and then that'll go into a further review process. And so this turns out to be really powerful, and it's a very scalable way. And so we actually run this on every single data point. Okay, so we talked about measuring and increasing the labeler quality, measuring and increasing task quality. The third one is instructions, and this is really, really important. So just like we decompose complex problems into simple pieces, we actually also decompose the instructions into simple pieces, because every task needs instructions, and we have an automated way to take the aggregate instructions and decompose them into smaller instructions. And so what we do is we have what we call a master instruction data program, which takes the instructions, decomposes them via the data program, and checks the quality. And so this is actually a data program in itself, so kind of a meta data program. And so what it does is it assesses the quality of the instructions on the task level and also on the aggregate level. And so maybe it uses humans, maybe it uses machines. That's up to the data program. But this turns out to be important. And related to this master data program, we use the internal audit team, mostly for our enterprise customers who need really, really high quality. But we also have NLP classifiers to check the syntactic and semantic structure of the instructions, and we use bots to run what you can think of as unit tests through each of the tasks. But in this case, the bots are humans, and so we'll run different variations of the task to make sure instructions make sense. Okay, and then finally, if you have really bad data, then no matter how good your data program or AI compiler is, you can't expect high quality. And so it's really important that you can automatically assess the quality of the data. And so I'll talk about 3 ways here. So the first is the data linter. So what the data linter does is it detects and suggests, it detects common errors and suggests improvements. So we use some off-the-shelf software for this, which works really good, but this can detect if you had unit changes or there's just some salient error for that and can suggest improvements. And then we have noise models. So this is particularly important for unstructured data. So we apply noise models and look for the signal to noise ratio, and if it's off the charts, then we flag this and it goes into the review process, which is this master quality data program. And so just like we had the master instructions data program, when we're assessing the quality of the data, we send the data into the data program, compose it into tasks, and if the tasks aren't high quality in addition to the input data, then this gets flagged and it's shown to you that this is low quality, and you can upload new data, etc. Because this is important because it's not always obvious that the input data is low quality. It could be that it appears high quality, but when you run it through the data program, you find that in a case that wasn't obvious, it was low quality. Great, so that was an overview of some ways in which we do quality assurance. The next video is another how video. It's going to go into a very important detail of data programming called our schema. See you then.